Hello, I'm August Gudmundsson. I'm going to talk to you today about a very important problem in volcanology, namely how do dikes form their paths from the source, the magma chamber, to the surface to feed volcanic eruptions. Now, one of the main unsolved problems in solid earth geosciences is to provide a theory, a reliable theory that allows us to forecast the propagation paths of any kind of rock fracture. Why is this important? It's important because this is a basic problem in structure geology, tectonics, earthquake mechanics, plate boundary initiation and development, landslides, various applied fields such as in petroleum geology and geothermal and hydrogeology, and of course in volcanology. So here I focus on dikes, as I said, and you could ask why. Well, because dikes and inclined sheets supply magma to nearly all volcanic eruptions on this planet. So it's of fundamental importance to understand the conditions for dikes like this one here in Santorini in Greece, the conditions that allow such a dike, a magma-filled fracture, to reach the surface. As I say, most volcanic eruptions on this planet are supplied with magma through magma-filled fractures, that if they're vertical, we call them dikes, and if they're inclined, we call them inclined sheets. Here we see a beautiful example of that in Kilauea, where part of the dike has reached the surface, the one just below the helicopter, whereas other parts are on the way to the surface. There are already fractures formed, and there is vapor coming up there, but the dike front, the magma front, is still under the surface. It's maybe a few tens of meters down in these tension fractures that the dike has formed. So where do we stand now as regards reliable forecasting of eruptions fed by dikes? Well, we have a recent example from Iceland in Bárðarbunga in 2014 and 15. Despite very detailed modern monitoring, including seismometers, geodetic studies, INSAR, GPS, and geochemical studies, we were neither able to forecast the propagation path of this 50-kilometer long segmented dike, nor were we able to forecast whether or not it would erupt, whether or not it would reach the surface. It did reach the surface, but the resulting fissure was very short, initially around 1,500 meters, and for much of the eruption, which lasted many months, it was only about 700 meters long. You see the fissure here. So the situation today is that we can't forecast whether, where, and when a volcanic fissure is likely to form when a dike is propagating inside the volcano during an unrest period. In addition, we cannot forecast this eventual size of that kind of volcanic fissure if it forms. Now, if we want to model dikes, if we want to understand dike propagation, the first question we have to answer is, what kind of mechanical fracture is a dike? And the only way to answer that question is to go into the field, like we see here on the left-hand side, to go into the field and check what kind of fractures are we dealing with. And cross-cutting relationships, as we see here, so here between the dike and the lava flows, this is northern Iceland, and you see the dike cuts through the lava pile, a few 100-meter thick lava pile. The cross-cutting relationships show that in most cases, the dikes are pure extension fractures. They are formed by pure opening. It's the magma that fractures the crust, forms the fracture, and opens it up due to the magmatic overpressure. So I would say in perhaps 98% of dikes I have studied in my life have turned out to be pure extension fractures. And when a fracture, an extension fracture, is formed by fluid pressure of any kind, water, magma, gas, whatever you like, we call it hydrofracture, a hydrofracture. So here we have a 6 meter thick basaltic dike in northern Iceland, many million years old, exposed at around 1.5 kilometers depth in the crust. It's an old rift zone, and it went straight through. That is not always the case. So we go further here and we look at other cross-cutting relations. Here is a cross-cutting between a dike and an inclined sheet in Ardnamurchan in Scotland, a famous fossil volcano in Scotland. And there is no doubt here that there is no displacement. It's pure opening where the dike cuts through the inclined sheet. Then we move on. Similarly, here in southern Iceland, we have a dike, an inclined sheet, another inclined sheet, and the dike. They're all meeting here, and the relationships are obvious. This is pure opening, pure mode 1 cracks in all cases. In all cases, what we have seen so far, it has been pure opening, pure mode 1, but of course, occasionally we see dikes going into existing faults. We have an example of that here is in Western Iceland, where the dike uses an existing steeply dipping normal fault as a part of its path. Now, when does that happen? It depends on the tensile strength of the fault in relation to the tensile strength of the surrounding rock and the dip of the fault and various energy considerations that I discuss in detail in my book, Volcanic Tectonics. I come to that later. So we can easily decide basically under what conditions a dike, a magma-filled fracture, would use an existing fault rather than forming its own fracture. So, as I said, not only are cross-cutting relationships among dikes and inclined sheets, indicating that most dikes and inclined sheets are pure extension fractures. We see it beautifully in this well-exposed lava pile in southeast Iceland, where we are standing. We are roughly 2 kilometers, 2,000 meters into the old crust, and we see a lot of regional dikes, mostly around 5-6 meters thick. And the dikes cut through the lava pile, and if one looks at the intersection, the cross-cutting between the dikes and the lavas, we see that there is no displacement up and down, and one can see by going there's no displacement in the horizontal direction. So these are pure extension fractures. The dikes are not, they are not using existing faults. So what is an extension fracture? In fracture mechanics, we call them mode 1 crack. It's pure opening. Mode 1 is pure opening. And the opening is perpendicular to sigma 3. So the fracture plane is perpendicular to sigma 3 and parallel with sigma 1 and sigma 2. Now that's extremely useful because it means we can model the dike propagation using sigma 1, the ticks or trajectories of sigma 1, as an indication of where the dike would be likely to go. And I'll show you numerical examples of that later in this talk. So again, just to remind you, a hydrofracture is a mode 1 crack, is an extension fracture. Its plane is perpendicular to sigma 3 and parallel with sigma 1 and sigma 2. Now sigma 3 is the minimum principal compressive stress or maximum tensile stress. Sigma 1 is the maximum principal compressive stress, and sigma 2 is the intermediate one. So tens of thousands of human-made hydraulic fractures are also primarily extension fractures. So we have plenty of evidence from the field for dikes and incline sheets and for hydraulic fractures made in industry that these fractures, the fluid-driven fractures, are extension fractures and formed in the plane that I indicate here. Second question is, how is the dike fracture formed? Do we have, at many kilometers depth, where the magma is propagating in dikes before it reaches the surface, do we have large-scale tectonic tension fractures like this one here in Þingvellir in southwest Iceland? This one is up to 10 or even 15 meters in aperture opening. Absolutely not. Absolutely not. There are no fractures, large fractures waiting for magma to fill them at many kilometers depth. First of all, observations over decades show that such fractures do not exist, even close to Þingvellir. I've studied that for many, many years. You don't find any large-scale tension fractures at depth of hundreds of meters or kilometers in the vicinity of this area here. And secondly, the so-called Griffith crack theory, which is the basis of fracture mechanics, shows very clearly that a pure tension fracture, and not a fracture filled by fluid, but a fracture formed by pure tension, so negative sigma 3, cannot exist deeper in the crust than a few hundred meters usually. Maximum absolute depth would be maybe 1 kilometer, but for common tensile strength, which is T0 here, the depth would be perhaps 250 to 500 meters. So below that, there are no tectonic tension fractures available for magma, which means the magma forms its own fracture. It is the magmatic overpressure that breaks the rock and forms the fracture. It is the magmatic overpressure, we sometimes call it driving pressure or even net pressure in engineering, breaks the rock and forms the fracture. And fortunately for the dikes, in that sense, rocks are very weak in tension. They are easily broken in tension. They're strong in compression, but they're very weak in tension. Let's move on. So since they are mode 1 cracks and can be modeled as mode 1 cracks, they are much easier to deal with, the dikes and the inclined sheets. They're much easier to deal with as regards modeling than faults, because faults are shear fractures and those are much more complex to deal with. Here we see, for example, something that we commonly see in the field, an abrupt change in the attitude, in the strike and dip. Here in mainly the dip, you can see changing, the inclination changing of an inclined sheet going up, meeting a lava flow, and then flowing under the lava flow for a while, where there's a contact between lava flow and a lake sediment. So again, I've showed you this one before. We see beautifully here that there are many dikes that are relatively straight when they cut through a lava pile where most of the lavas have similar mechanical properties. But that is not always the case. It's not always the case. As I said earlier, the average thickness of the dikes here is 5 to 6 meters. The maximum are 10 to 15 meters. So some dikes are comparatively straight on the left-hand side here, but many, particularly inside central volcanoes or stratovolcanoes or volcanic edifices, polygenetic volcanoes, Some of them show abrupt changes in their attitude when they meet layers of contrasting mechanical properties, as we see on the right-hand side. We see a close-up here. The dike on the left-hand side comes up to a contact between mechanically dissimilar rocks, changes for a while into sill, you see the man here for scale, and then finds a new path as a dike again on the right-hand side. This is something very commonly seen in the field and indicates changes in the local stress field and in, of course, the mechanical properties of the rocks. Similarly here in Southeast Iceland, this is an old, tiny acid or felsic magma chamber, and we see the dike injected from the top of the magma chamber and then forming a zigzag geometry because it comes to contact with the lava pile, shifts to the right, and then continues further up in a zigzag way. Another dike is more straight on the left-hand side. The roof of the old magma chamber here is a basaltic lava pile. Again, this is what you see in the field. Here's a dike, or possibly we could call it an inclined sheet, coming up, meeting a contact between mechanically dissimilar rocks and being shifted to the left as a sill. So abrupt changes in the paths of dikes and inclined sheets are very common, particularly inside fossil or active polygenetic volcanoes. We see examples here from Iceland and from Tenerife. The Tenerife one is in the upper right corner where the lady is standing. So what happens in active volcanoes? Here is an artistic interpretation of what may have happened inside Eyjafjallajökull, the volcano that erupted in 2010 in southern Iceland and caused a lot of problems for the air traffic. Of course, these vertical pipes are very much a artistic interpretation and probably not very realistic, because sills would normally be fed by dikes. But anyway, for 2 decades before finally the eruptions happened in this volcano, there were many dike injections, and apparently based on geodetic studies, those seismic ones, those dikes changed into sills at various depths inside the volcano and in the crustal segment below the volcano. So basically here, we have many sills forming over 20 years period, and then finally 2 dikes made it to the surface, one giving rise to a tiny eruption of no consequence, we called it the touristic eruption, and the second one going through a shallow magma chamber with more evolved magma and going through the glacier and causing eruption clouds or columns and a lot of troubles for the air traffic. And we would not be surprised. We would not be surprised, because if one looks into the southern flanks of this volcano, Eyjafjallajökull, there are plenty of sills and dikes there. Plenty of sills and dikes. And the volcano is highly heterogeneous in its composition and in its mechanical properties. You have stiff or hard or high Young's modulus sills and lava flows. You have much more compliant basaltic breccias that we call hyaloclastites, and you have pillow lavas and various other things. So the variety in mechanical properties is extremely high in this volcano. So the tendency to form sills is also great. We see it very clearly here, and even better on the next one, this one here. This is the same, the southern slopes of the southern flanks of Eyjafjallajökull, where you can see lava flows, hyaloclastites, dikes and sills, and pillow lava at the bottom. That means that the contrast in mechanical properties is very great in this volcano, and therefore the tendency to sill formation, for dikes being deflected into sills, is very, very great indeed. Now, observations of dikes, and in fact fractures in rock fractures in general, show that they are normally segmented. On the left-hand side, we see two segments of a dike in Santorini in Greece. In the central part, we see two overlapping, A and B are overlapping segments of a dike in Tenerife. And on the right-hand side, we see two, again, overlapping and forming a hook-shaped segments of an inclined sheet in southwest Iceland, as your person there for scale. The segments are seen beautifully here in a regional dike in northwest Iceland, a 5 meters thick dike. You can see that there are some sheep standing on the coast here. The dike is very long and is clearly segmented. I just show the 6 closest segments, but there are of course many more, as you can see when you look further on the strike of the dike. How does the magma flow in the dike? It can flow vertically into all the segments, as I indicate on the upper corner left-hand side illustration. But in some cases we have the fracture itself propagating laterally, whereas the magma is rising vertically, mainly due to buoyancy, as forming fingers, and the first finger to reach the surface, of course, would cause something like we see here in Hawaii in 2011 in the lower illustration, and in Iceland in 1980 in the lower right-hand illustration. So, of course, for all dikes that reach the surface fissure must propagate laterally, even if the magma, of course, there is coming up vertically. So most volcanic fissures, they start like we see here in Hawaii on the left-hand side and Iceland on the right-hand side. They start like little fingers, maybe a few tens of meters long, and later on they develop into kilometer scale or even tens of kilometer scale volcanic fissures. So obviously the fracture itself has to propagate at the surface laterally. So we see them offset, but we see also, and segmented, but we see them also arrested. Here is one dike arrested in Tenerife, and this segment obviously has a tip, exposed tip or top, and never reached the surface. Well, not a feeder, it's a non-feeder. And the great majority of all dikes are non-feeders. They never go to the surface. They become arrested at various crustal depths. They're pure intrusions. I'll show you here just a few examples of arrested dike. Here's one, thin one, 0.4 or 4 meters or 40 centimeters in Santorini, in the colder walls of Santorini in Greece. It is arrested at the contact between a lava flow and scoria. So the lava flow is stiff, hard, high Young's modulus. The scoria is relatively compliant or soft and low Young's modulus. And that's an ideal situation for arresting dikes. So this one obviously this segment did not make it to the surface. Similarly in Tenerife, a dike going up through a soft layer, pyroclastic layer, meets a contact with an existing inclined sheet, which is stiff and becomes arrested. So there are basically 4 possibilities for a dike meeting a contact. In A, it becomes arrested, stops altogether. In B, it penetrates, so may theoretically continue up to the surface. And in C and D, it becomes deflected in one or two directions in the vertical section, forming a sill. Now the question is, in B and in general, how does the dike decide on its path? How does the dike decide where it's going? And that's, of course, is the main theme here. How does a fracture, in this case we are talking about an extension fracture, how does it know where it should go? How does it decide on its path? Theoretically, at the source or at any particular place in the crust where the dike stops and then continues to propagate, it has an infinite number of possible potential paths. So here from the source in 1 to the surface or the place where the dike would be arrested, there is an infinite number of potential or possible paths. And the question is now again, which of A, B, C, D, E, F, G, H, and to infinity, which of these paths would the dike choose? And why? What is the criteria? When dikes propagate, it's important to remember they propagate in steps. Here I show 10 possible theoretical steps for a dike going through a lava pile in northwest Iceland. So in each case, the dike fracture front, the tip of the dike fracture itself, propagates very quickly, say 3 kilometers per second, like an S wave. But the magma has to follow the dike fracture. So the fracture propagates very quickly and then stops and waits for the magma front to follow it, to fill into the fracture tip. And then it can propagate again. So the overall rate of propagation of dikes is very slow. It is similar to a pacing person, to the way we walk, the velocity we walk at. But the individual fracture propagations ahead of the fluid front at each time, they are very rapid. But as I say, they have to wait for the magma to come in. So again, each step, each segment has, strictly speaking, as we see here again in Santorini, each has a possibility of an infinite number of paths. And how does it select the one? Here, number 4, or segment B, how did it decide to go along path 4 instead of, say, 1, 2, 3, 5, 6, 7 here, from point A, where it probably stopped, to point C, where it's a new segment taking over? How did it? The answer is it selects the path of least action, More specifically, the path satisfies the Hamilton's principle of least action. Now, what do we mean by Hamilton's principle of least action? I will show it to you mathematically or physically in a moment, but I will explain to you also what it means in general terms. For dikes, because they propagate slowly and the kinetic energy is not of very great importance, Hamilton's principle of least action in reality reduces to a well-known principle from mechanics or continuum mechanics, the principle of minimum potential energy. So this is Hamilton's principle of least action. This one here is, strictly speaking, for a discrete system, that means system composed of particles. In this case, T is the kinetic energy, V is the potential energy, and the symbol L is what we call the Lagrangian. Now these guys, Lagrange and Hamilton, were mathematicians. But in the old days, mathematicians often worked in what we would call theoretical physics today. So they were mathematicians and theoretical physicists in a way. So action has the units or dimensions of energy and time, energy multiplied by time, or linear momentum times distance. And the unit is joule second, joule second. Now, strictly speaking, what this means is there is an extremum or extreme. That does not necessarily mean that the energy transformed is minimum, but in most practical cases, the energy transformed times the time taken to propagate would be a minimum, would be least. That is the reason we call it principle of least action. Principle of least action. This is my second slide of some physics. So after that, I will not continue with these formulas. But just to explain to you, the equation I just showed you was for discrete systems, a system composed of particles. Now, obviously, the Earth's crust is composed of particles, but it's a continuum. It's a continuum. And the Hamilton's principle for continuum mechanics says that the difference between the kinetic energy and the combination of the strain energy and the potential energy is an extreme or minimum in most cases. And when we can drop T, the kinetic energy T, then it reduces to the well-known principle of minimum potential energy. What does that say? It says simply that of all the possible displacement fields or configurations that an elastic rock body could have during dike propagation, the one that is actually reached or satisfied is the one where the potential energy is a minimum. Now, this is all very theoretical, and we know in geology we are not, many of us are not very keen on these kind of topics. So let's see if we can rephrase this in very easily understandable general way. So the general way to say it is that dikes and sheets and other mode 1 cracks, extension fractures, are basically lazy. They always go for the easiest path. That is the path that requires least energy and time. And when kinetic energy is not important as for dikes, they would go for the path of least energy. I sometimes say, as a kind of joke, that there is a sort of a cosmic laziness principle that they follow, and this principle is extremely wide. It applies not only to dikes or fractures, it applies to a lot of processes and things in nature, in physics particularly. It's one of the fundamental problems, one of the fundamental principles in physics. One of the fundamental principles in physics, and used in a variety of fields in physics. So here we see 1 to 2, the thickness changes, 1 to 2 meter thick feeder dike in South Iceland, ending in the lava pile. This is the South Iceland. But why is energy needed? What is the energy used for when a dike is propagating? It is needed basically for 2 things. 1, to rupture the rock. That's called surface energy. And 2, to open the fracture, to move the fracture walls against the pressure, the stress of sigma 3. And the principle of least action or principle minimum potential energy implies that the dikes propagates in the direction of combined least normal stress, which would normally be least sigma 3, and least tensile strength, or we can formulate it also in terms of material toughness. So this path is the path of least action or minimum potential energy. And that's the path the dike selects. Out of infinite number of paths, it would select this one, and it always does. Again, just to remind you, these abrupt changes here in the paths of dikes and incline sheets are therefore a consequence of the fact that the dike is looking for, trying to find, following the path of least energy, minimum potential energy. That's the reason it shifts suddenly to a thin sill and becomes a dike again, or becomes a sill under a stiff lava flow, and then continues as either a dike or inclined seat. But even if many of them have irregular paths, we have discussed earlier that many dikes in a reasonably homogeneous lava pile where all the rocks are of similar mechanical properties, many dikes there are straight or reasonably straight. As we see here in eastern Iceland, here we are around 1,200, 1,300 meters into the lava pile. In this photo I also had shown, and I kept it, the measurement line where I walked along the across or along the dike swarm here. There's a part of a dike swarm to measure the dikes. Most of the dikes here are around 5 meters thick, and the white arrows indicate, each of them indicates a dike. So here we have this dike swarm, and we can see clearly that they are reasonably straight, and the same here as we have seen many times. Here they are reasonably straight again. So what do these principles that we have now established for dike propagation paths, what do they tell us as regards real volcanoes? Here we have simplified, but we could say a real situation in an active volcano. We have a shallow magma chamber here of circular cross section, and we have a homogeneous crust. That means that there is no real mechanical layering. Of course, this is simplification, but let's start in this way. And then we see immediately that the dike paths, they follow these ticks. The ticks are sigma 1, the maximum principal compressive stress. They follow the ticks. And the magma paths, which could be dikes as well, from the deep reservoir, they also follow that, these ticks. And that means that in this situation, the shallow magma chamber would act as a sink. It would collect magma from a wide area of the reservoir, of the deep reservoir underneath, channel it into the shallow magma chamber itself, so receive it as a sink, and then expel it to a much narrower area at the surface as dikes. And the dikes again follow the ticks here of sigma 1. And at the surface then, the volcanic edifice would form. So the magma chamber draws in magma from a wide area of the reservoir, the deep reservoir underneath, and channels it to a limited area at the surface where the volcano forms. This is the reason we have big polygenetic volcanoes. In the last illustration, the only loading, the only pressure, strain, or displacement was pressure inside the magma chamber. There was, in fact, excess pressure in the chamber as the only loading. Here we have a different loading. Here the only loading is tension, extension, acting on the magma chamber. Could be situation in rift zone, for example, or divergent plate boundaries. And you see the paths here, both the magma paths from the deep reservoir and the paths of the dikes that go to the surface or become rested possibly, have a much narrower range. So in this case, the magma chamber would receive magma from a more limited part of the deep-seated reservoir and channel magma to a more limited area at the surface. But of course, homogeneous isotropic models are very unrealistic. So here we have a different model where we start by just a tiny bit of change in the mechanical properties of the layers above the magma chamber. Here, what I did here was to take a magma chamber and have 10 layers above it, where the Young's model is the stiffness, the hardness in a way, of each layer increases by 2 gigapascal from one layer to another one. And even if there is such a very slight change in the stiffness with depth, the paths of the dikes become much more irregular. But in the center, it stays more or less straight. But in the margin areas, it becomes much more irregular, and we start to see dike, sill, dike changes as I indicate here. And when we go into more realistic models where there's a sharp contrast in the mechanical properties between the thin and thick layers, as here, we start to see what we really observe in nature. If we look at D, that's an inclined sheet arrested in the second layer there, the thin layer. In B, there is a dike deflected into a sill and then becoming arrested. In A, the dike becomes arrested immediately. And in C, the dike changes into a sill and then continues as an inclined sheet. So all the ticks here are showing the orientation of sigma 1. Why do the dikes change in this way into sills? Because they have to follow the ticks. They have to follow the orientation of sigma 1. If sigma 1 becomes rotated 90 degrees, then if the dike has any chance to continue, it must rotate itself. So for a vertical dike, it must change into a sill, horizontal sill. If the inclined, if the ticks of sigma 1 become inclined, then obviously you will get an inclined sheet. So it's basically very simple. Here we are assuming the tensile strength of the rock is more or less constant, which is basically the case in most situations. So if we now go into the same situation, but the only difference is that we have, instead of a sill-like magma chamber, we have one with a circular cross-section area. You see similar results, but not the same. The deflection occurs at different places. The deflection of dikes into sills and the arrest of dikes occurs in the middle of the model in B and A and C, rather than close to the surface of the magma chamber, as we saw in the last one, where there was an inclined, where the magma chamber was sill-like. So the situation could be similar to this one here. I showed very schematically here on the right-hand side. The dike would go in from the magma chamber. The dike would go in from the magma chamber, and things are going very well. It continues through the red layer and continues through the blue layer. Everything is going well. Here, the ticks have rotated, flipped 90 degrees. So either the dike becomes totally arrested at the top of the red layer, or it becomes deflected into a sill. So let's say it becomes deflected into a sill. That will depend on the overpressure of the magma. Here's it deflected into a sill. Now it reaches a region where the ticks are inclined, so they would go up as an inclined sheet. And where it would go from there, we don't really know. And one has to be careful that we are reaching the limit of the numerical model where the results are affected by the way we fasten the model, so we wouldn't carry it further. This extension here would then be an indication that we can go to the end of the model, but as I say, we would normally not do it. We would have stopped earlier and say, what is the left on the left-hand side here, which I added, is probably not realistic because we are coming close to this X in the top where the model is fastened, and that fastening, which is artificial, affects the stress trajectories. Some dikes, as I said earlier, maybe a few percent, they use existing faults. Now, what kind of faults would they use? Based on theory and observation, they would normally use very steeply dipping faults and probably most commonly normal faults. We can easily calculate under what conditions it becomes economic, easier, requiring less energy for the magma to go into an existing fault and follow it for a while rather than form its own fracture. The basic thing to look at is the stress on the fault, sigma n, the normal stress, which of course depends on how deeply dipping the fault is, and the tensile strength of the fault in relation to the tensile strength of the surrounding rocks. So if the tensile strength of the fault is extremely low or zero, the fault has recently been active, the chances for the magma to go in there, for a while at least, is higher. But as I said, this is very rarely seen. In this illustration, I also indicate here that the dike fracture propagates ahead of the fluid front. So the magma front is behind. There is often a cavity for a while that needs to be filled by the magma, and the magma flows slowly because of viscosity. That's the reason the dikes propagate relatively slowly. So here's a numerical model showing that dike coming close to a fault or any kind of discontinuity or contact even would tend to open that contact or fault in an asymmetric way. And then depending on the energy considerations, it might go into the fault for a while and use it as a part of its path before continuing to form its own path towards the surface. Here again, I show you an even more realistic model where we have 30 layers with different mechanical properties. You see the ticks, sigma 1 ticks, they flip commonly, they rotate, become inclined or flip 90 degrees. And as a consequence, the paths of the dikes would depend very much on where at the surface of the magma chamber they would initiate. We see here dikes 1, 3, and 5 would definitely become arrested. Possibly dike 2 and 4 would make it to the surface to supply magma to an eruption. So based on these principles that we discussed now, the least action or principle minimum potential energy, we can theoretically now reach the level of forecasting likely paths of dikes when there is an unrest period in a volcano with dike injection. How do we know there is a dike injection during an unrest period? Well, usually the best indication are earthquakes. As soon as the magma chamber ruptures and a dike starts to propagate, it forms an earthquake swarm, and we can monitor that swarm very easily. We can follow the dike by the earthquake swarm. So these ideas, of course, and models need to be tested further in the future, particularly using earthquake swarms as an indication. And we need, of course, to know the mechanical layering of the rocks in the volcano. When we are dealing with active volcanoes, the information we have is usually from steep sea cliffs, cliffs in collapse calders inside the volcano, or from drill holes. And I think in the future, most of all dangerous volcanoes in the world will have deep drill holes to monitor stress and strain and to have an indication of their mechanical layering. So that would help us to forecast realistically the likely paths of dikes injected during unrest periods. So to conclude, field observations and in fact theory demonstrate that dikes are primarily extension fractures and should therefore be modeled as mode 1 cracks. They propagate as segments in lateral and vertical sections, And what we've observed is that in the lateral sections, the offset, the distances between the segments are usually smaller. They're better connected than in the lateral sections. Number 3, most dikes become arrested. This is very important. Most injected dikes are non-feeders. They do not lead to an eruption. This is fundamentally important, because in most unrest periods with dike injections, we would therefore not expect eruption to occur. And that's something we really need to keep in mind. Now, the propagation paths of dikes and other extension or mode 1 cracks or fractures can be forecasted in principle using the Hamilton's principle of least action, which for dikes can be reduced to the principal minimum potential energy. So in combination with numerical models and field studies and measurements during the unrest periods, and of course we need information about the mechanical layering in the volcano, we should theoretically be able to forecast the likely paths. For their full potential, numerical models of dike paths require this detailed information of the mechanical layering, and as I said, that layering, even in active volcanoes, can often be obtained from drill holes, from caldera walls, from sea cliffs and other exposures. And I think or hope that in the future, all really dangerous volcanoes on this planet will be with drill holes for monitoring stress and strain, and for obtaining information about the mechanical layering that can be used in this kind of modeling. Those of you who like to go deeper into this topic, I should refer to chapters 7 and 10 in my book on volcanotectonics, where I have a lot of calculations and many worked examples for people to exercise their skills and understanding on. And with those words, I say simply, thank you very much indeed. Bye-bye.